A very good afternoon and welcome back one and all present. It takes nothing to join the crowd, but takes everything to stand alone. I call upon B. Sorna of 3rd year Biotechnology Department to deliver the guest introduction of our guest who took every single step to stand alone.
A warm welcome to one and all present in this virtual workshop. I am very happy to have a chance to introduce our guest, Dr. D. Michael Emmanuel JC, working at Assistant Professor, Department of Biotechnology at St. Joseph College, Tiruchirappalli. He has completed his BSc Microbiology in Comrade College, Thoothukudi. He got his master degree in MSc Biotechnology and Bioinformatics, Faculty of Science and Humanities at SRM University, Chennai. He has completed his PhD in University of Madras, Chennai. He also has experienced as Senior Research Fellow, ICAR and CAAR Andamans, and Project Fellow, University of Madras, Guindy, Chennai, and Postdoctoral Researcher, Sujan National University, South Korea. And now he is currently working at Tiruchirappalli. He has totally published 28 research articles and 1 book, and he has organized 4 conference presentations, 4 oral presentations. Today he is going to teach us under the topic molecular docking, so that the next 2 hours will be very more interesting than we think. I welcome you, sir. I am so proud to welcome such a great person. Once again, I render my heartful welcome to you and welcome one and all. Thank you.
Thank you, Sorna. I'm really delighted to call upon our guest, Dr. D. Michael Emmanuel Jesse, Assistant Professor, Department of Biotechnology, St. Joseph's College, Tiruchirappalli, to handle the session based on the topic molecular docking of a natural inhibitor against COVID-19 spike protein.
Yes, thank you, ma'am. Am I audible?
Yes, sir.
Yes, sir.
Okay, so thank you so much for calling me in this great program. So I am glad to share some of the topics in Autodock Veena and Autodock. Already in the first session, ma'am has clearly taken about the Autodock. So we can go to some advanced level. So in the morning session, we saw about only one compound, right? So now we can see more than one compound. If you handle more than one compound or more than 10 compounds, how you can manage the docking. So every time the morning session, you get nearly 40 steps. Okay, nearly 40 steps you have to do to accomplish one docking task. But when you go for 100 and thousands, and when you meet libraries, it is called virtual screening. Okay, so till 10 you can do it in Autodock, but beyond the 10 you don't have enough time to handle the tasks. Okay, so in this through this talk or through this workshop, you can handle more than 10, even 1,000, even libraries you can download from the databases and handle the docking tasks at limited time. Okay, so okay, first what we will learn here. I'm not going to much concentrate on molecular docking and like introduction. I'm not going to concentrate more on the introduction part, and I wish to directly go inside the procedure, because morning session ma'am has clearly taken what is molecular docking and Autodock. Okay, so let us travel to the this one slide I have for introduction regarding molecular docking. That is some prediction that here you are not going to confirm that this drug is always react with this molecule, but this is just a prediction. It is instead of a blind picking out the drugs, you can just predict the efficiency of the molecule, ligand molecule, to the yes, Gokul, anything? Gokul has raised a hand. Okay, so this is just a prediction of the association between two molecules, that is the receptor and the ligand molecule. Okay, this is the docking is the method which predicts the preferred orientation of one ligand. Okay, on the basis of orientation, which orientation of the ligand is the best to bind with the active site to form a stable complex. Okay, in this field we get the CAD. CAD means computer-aided drug discovery. So you apply the computer systems or the electronic, the whatever it is that you will apply in the chemistry part to calculate the properties of the future drug molecules. What you predict here, it goes to the wet lab, and then it is taken for synthesis of drug molecules, and then validate using clinical trial, pharmacokinetics, whatever it is. Okay, this is the basic for the development of a drug molecule. And fourth one is the identification of low energy binding modes. Okay, the binding energies is expressed in the negative values. The more the negative value, the reliable the drug is. Okay, it has higher affinity towards the receptor, the ligand within the active site of a macromolecule or a receptor. So this is totally binding affinity. So many ask about scoring and binding energies. Okay, so many software they don't give binding score separately and binding affinity or binding energies separately, but Schrodinger will give binding score separately and binding energy separately. So the scoring, once the molecule is docked, once the ligand molecule is docked inside the protein, the docked molecule will give you the score. Okay, so that will calculate as energy. That combined calculation of all the energies is delivered to you as a binding energy. Okay, so how have anyone heard about International Space Station? International Space Station that is floating in the space. Okay, when some rocket or some satellite is sent or some spaceship is sent from the Earth, they first go and dock with the International Space Station. The process is called docking there also. Okay, that means the spaceship that is sent from the Earth, it binds with it couples with the protein. Couples with the spaceship, the space station that is already floating in the space. So that is also docking. Similarly, here also we have a ligand, whether it is fitting with the target protein or not. That is we are going to see here. There are two types of docking: rigid docking and flexible docking. Morning also the professor said about lock and key model. So in lock and key model, the lock is also fixed, the key is also fixed, fixed shape or fixed orientation, fixed conformation. It will directly binds to the receptor. Whereas in flexible docking, the ligand may be any conformation, but the receptor tunes itself to fit the ligand molecule. That is induced fit model. This is flexible docking. This is the case of flexible. So you have to remember rigid docking or flexible docking. In rigid docking, you are not going to specify any of the amino acid. Okay, you are not going to specify any of the amino acid in the active site. But in the flexible docking, you have to mention which is the spot you are going to bind the ligand. Okay, test the ligand. There are many algorithms are there. Matching algorithm, incremental construction, MCSS, LUDI, Monte Carlo, and genetic algorithm, molecular dynamics. We come under, that is the Autodock come under genetic algorithm, especially Lamarckian genetic algorithm. Many of you asked about what is the difference about genetic algorithm and the Lamarckian genetic algorithm. Genetic algorithm is a global search. Okay, it's a global. It examine the protein receptor, and then it will bind the ligand at a particular spot. If you do 10 or 20 times or 100 times, the ligand is going to bind to the same spot. Okay, that is restricted to that particular region. But in the Lamarckian, degrees of freedom is higher. See, for example, I read a story, the Mendelian theory, what it says, gene is the most important thing. Gene is going to determine your characteristics. Okay, the gene is going to, based on your gene, your behavior will be there. Based on your gene, your resemblance will be there. But in Lamarckian genetic algorithm, what it says, the Lamarck says that no, it is depending upon the individual character. Whether they can overcome the genetic traits, okay, they can overcome the genetic behavior. That is what Lamarck says. That is the difference between genetic algorithm and the Lamarckian genetic algorithm. So in Lamarckian genetic algorithm comes under the flexible docking. So flexible docking, you do a global search. In addition, you are going to do about the local search also. Local search, which amino acid you are going to give for the active site. That is the flexible docking. Okay. So in genetic algorithm, you cannot give. That is the rigid docking type of thing. Whereas in Lamarckian genetic algorithm, you can provide the active sites, and these active sites are flexible in nature, that it at different conformation. For example, after Autodock, you get 10 different conformations. So the that amino acid molecules, atoms, everything tune itself. They are flexible to adjust the conformation of the ligand. Okay, that is the Lamarckian genetic algorithm. I hope you are clear. Okay, so it is local search. Lamarckian genetic algorithm is also a hybrid algorithm. It combines both the global search and as well as the local search, which is not the case in general genetic algorithm. Okay. So now we come to Autodock and Autodock Vina. What is the difference? Okay. So scoring function is the main difference in Autodock Vina. Autodock, they use Amber, but in Vina they use hybrid. They are empirical and knowledge based. Okay, so the speed is also slower in Autodock, the general Autodock, and Vina you can do much faster than the Autodock. The binding mode predictions is less accurate in Autodock and more accurate in Vina. Okay, the threading also, Autodock sometimes they cannot use if you having multi-threads, but Autodock cannot able to adapt to the threading properties of your the configuration. Okay, threading configuration of your system. But in Vina, it adjusts. If you have 8 core, it will replace all the 8 core. If you have 12 cores, it will use all the 12 cores to increase the speed. Okay, so here, so this is directly taken from the literature, that what are the advantages of Vina over Autodock. Okay, so it is faster and easy to use, more accurate. So you no need to follow those 40 steps in Autodock 4. Okay, like that. The only disadvantage, the algorithm and scoring function, you cannot depend upon. But when you prepare the ligand and the protein prior to the docking, then the efficiency will be higher. Okay, however, you can dock a high quality complex. Okay, so virtual screening, there are many libraries are there, and from the libraries you are going to screen at least 4 or 5 useful drug molecules. Okay, so when you come under virtual screening, that computational cost will, okay, so it will whatever it is, so you cannot afford for all the drug molecules. So when you screen more, when you concentrate the ligand molecules, you can able to narrow down and increase the quality of the ligands also. So many of you don't know what is molecular simulation. So what is that word simulation? You don't know. Okay, so when a pilot, okay, for a aeroplane or flight, when a pilot they are getting trained, they are not directly going to sit inside the aeroplane. Okay, instead they will be given some platform like this. They will give some virtual thing, and there you have to operate the flight, or this is a kind of this is car simulation, or like this you have to simulate first, and then you get trained. After getting trained, you are directly applying it in the aeroplane. Similarly, the outer environment, the environment where the drug survives, or where it going to react with the receptor, that you are going to simulate in the computer. Okay, in your computer, then you are taking it to the system. That is the that is called simulation. Okay, and what are the steps involved in molecular docking? First thing is retrieval of ligands and its processing. Second, receptor processing. Third, you have to identify the active site. Fourth, docking. Fifth, the analysis of your docked complex. And sixth, you are going to analyze the pharmacokinetic property of the ligand. Then you have done it. Okay, so pharmacokinetic analysis you already heard about and then studied in your theory part. The ADME concept: absorption, distribution, metabolism, and excretion. Okay, so these things you are going to, how you are going to check for your ligand. Okay, so this pharmacokinetic analysis you can do here or you can do before docking also. Okay, you can screen based on this pharmacokinetic property before docking also. That is your choice. And retrieval of ligand, from where you can retrieve ligands. In the morning session, you retrieve from PubChem. So similarly, other databases are there, chemical databases, PubChem, ChemSpider, and EMBL, and then finally Drug Bank. Okay, here we can consider PubChem because most of the ligands are deposited in the PubChem. So it is standardized and it is used throughout the world for the research. Okay. So if you have any questions till here, after this we will be going for practical. Do you have any questions here?
Yes, sir. Good afternoon, sir.
Good afternoon.
Sir, while retrieving the ligand, we are getting from PubChem, ChemSpider, these things.
Yes.
Is it okay? How to minimize the energy of the ligand? How to optimize the ligand for
Yes.
getting into docking, sir?
Yes, I will be taking that one. Then I'm asking before the slides. If you have any doubt, you can ask.
Okay. Thank you,
So
sir.
now I'm threading means Praveen Kumar has asked threading. Normally in your laptop, the system you will be having, there will be maybe some 8 threads. 8 threads means your RAM will be split into different blocks. You can see. So in supercomputer there are multi-threading. There will be many number of processors and there will be many cores. Okay, cores means the job you are giving, that is distributed throughout to all the cores individually. Okay, all the cores will take the job individually and they will speed up the process. Okay, so many supercomputers, they rely on supercomputers because of the multi-cores and multi-threading. Okay, so if you go for Linux, then you will understand what threading is. Okay, so usually supercomputers, they operate in Linux only, because now I am using Windows. Some other time, if time permits, we can show the Linux also. Okay, so this will be easy. I'll take. Okay. Any other questions? Okay, then I proceed for the ligand retrieval. Okay, for example, I take 3 ligands. Okay, you can take any number of ligands, but here for your time constraint and for your understanding, I take 3 compounds: imodine, quercetin, and piperine. Okay, so I think you all know the sources of these compounds. Piperine, you know, pepper; quercetin and imodine from frangula bark, and quercetin, I think it is from onion. The onion you use, no, that is PubChem. Similarly, here also, because for your convenience, I didn't download the structure yet. Okay, I download it. You are going to see everything what I do. Imodine, just click the imodine, and here you have, no need to concentrate here and all. Okay, just check what is the molecular weight, and when you download the ligand, if it is below 500, below molecular weight below 500, it will be more easy for the system body, the human body, to absorb the drug. Okay, it is easier for the human body to absorb the drug. The absorption rate is higher for lower molecular weight substance. So usually prefer low molecular weight ligands. Okay, here I put E mode in. Already morning you saw HDF. See, then I go for quercetin. If I am fast, please stop me, okay? And third, what else? Piperin. Okay, here is an okay, I have downloaded 3 structures and I directly go for this. Then I directly go for energy minimization. So this you can skip because you will also do energy minimization in Autodock Vina also. Okay, but here you have to learn this software. What is this? How you have to do the energy minimization in COMMENT 3D. So I am teaching you this one. Okay. So if you need the softwares, you please ask me, I can send you. So this is Chem Office. You have to give the enable hardware acceleration for this session only. Okay, this will use maximum of the RAM. Okay, so this is the space. Here I am going to load the structure. So I have emod in first. So usually there is you have to apply the molecular mechanics in this structure for energy minimization. So here in this calculation, just select or Control A. If you give Control A, it is selected like this yellow. Then you can go to calculation. There are 2. No, see MM2. This molecular mechanics 2 and molecular mechanics force field 94. Okay, these 2 are there. You can use this MM2. Okay, go to minimize energy. I hope you are following. No.
Yes, sir.
Okay, so here RMS, the root mean square deviation. Okay, here you have to give 0, 0, 0, 0, 1 is okay enough. 0.001. So see, I click run, the structure conformation will change. Okay, see how it is behaving like. Okay, now if you want for your publication, you can take this, the below, the steric energy details will be there. Stretch, bend, what is the bend and what is the torsion, what is dipole interaction. Okay, this you can copy it. Otherwise, no need. Okay, here again. Here again, molecular mechanics force field 94 algorithm is used here. So electrostatic calculation, Van der Waals calculation. If you run, it is run. Okay. And then again, you have to go to this. You have to calculate the charge of the ligand. Okay. So you have to go to extended Huckel, this option, and go to calculate charges. Okay. So you will get the charge for all the individual atoms. Okay. So here, so one of the important thing will happen. the deleting lone pairs, the lone pair of electrons will be deleted. That was formed in the previous MM2 dynamics. No? So in the molecular mechanics 2 algorithm, there must be some lone pairs must have formed. So when you calculate this external Huckel charge, the lone pairs will be removed. Okay. Now this is perfect and energy has been minimized. Okay. Now I will be saving this as PDB. Okay, emodding. So previously it was in SDF format. I opened it in Chem3D. Now I am saving it in PDB format. Okay. Okay. Next. Now I am going for a new compound. What is that compound? Piperin. Okay. Piperin. So now I'm not going to select the compound. Just you want to see the lone pairs here. Okay. Here you will see the lone pair. I'm giving minimize energy. Okay. 0.001 and just run. See, there is some pink color formation. These are lone pair of electrons. Lone pairs. Okay. This has to be removed. So the algorithm will minimize the energy till it becomes 0.000. Okay, 0001. Okay. Then calculation, you have to go for here, and then you have to run. See some steric. See the pink color has disappeared. So this has removed the lone pair of electrons, okay, which may interfere with the docking. So now it is okay. Now select all and save as piperin in PDB format. Okay. Now the other compound, third compound, quercetin. Okay. So if you energy minimize here, the quality will be better in your docking experiment. Okay. Minimize energy. And just pink color lone pairs. So in the previous version, there was another algorithm called MOPAC. Okay, so when they update, they have changed to Huckel and okay. Now the quercetin structure also it is ready. Okay, now we can close this. No need. Outcome also not needed. Okay, so now we have finished this step. So why this energy minimization is required? So the theory behind this is to remove the clashes among the atoms of the ligand. Okay, there may be steric clashes. Steric clashes, it will be removed. It will be aligned in such a way there won't be any clashes between the atoms. Okay, so every docking software they uses this energy minimized ligand for the docking algorithm. Okay, to apply their docking algorithm. Okay. So now we have to generate the conformation of each and every ligand. So we have 3 ligands: emodin, piperin, and quercetin. So we are now going to generate the conformers. Okay, so conformers can be generated using either data barrier software or gypsum. So if you use gypsum, you have to enter Python code. Okay, the Python script you have to enter. Better you use data barrier because it is just user friendly, and just a click and just with a click you can generate the conformers. Okay, I show you that data variable. Just open, you open. I saved the working directory as Autodock workshop. Here I have emodin, piperin, and quercetin. First I click the emodin. So you should be more careful when you should see what I am doing clearly. Okay, I may be fast. If I am fast, you ask me to repeat it. Okay. So the structure is loaded here. Okay, you can do single ligand also. Otherwise, you can combine the ligands. Okay, you can combine the ligands. See, I have the ligands here. Emodin. Okay, I have emodin, this PDB file, and piperin. I'll open in. Okay, I open all the thing in Discovery Studio. Okay, we have three things. Okay, three ligands. Okay, we can create the cluster of these three. I'm selecting all the three, and then I am saving it as SDF file. SD molecular, this one. Ligand. Okay, I'm saving it as like